Hello again. Thank you for joining us on Space Nuts Q&A edition. This is where we answer audience questions, or at least we read them out and pretend we know what we're talking about. Today, we will be answering questions about dark matter versus a black hole. It's a titanic struggle. Who would win? We're also going to discuss the demise of Betelgeuse or Betelgeuse, depending on how you like to pronounce it. We have a question about Lagrange points, and the Kordylewski plasma clouds question has come up from a YouTuber. We'll deal with all that right now on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Back again for more, has done all the research, has all the answers to all the questions except for those four. It's Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Good afternoon. How are you doing?
I'm all right. How are the Renos going at your place?
Oh, not too bad. I think they've clocked off for lunch at the minute, so we might get away with it. Although I'm waiting for Maya, the dog, to insist that I pay attention to her.
Yes, dogs do that. Yes, indeed they do. All right, let's answer some questions. Firstly, we've got a question from Howard. He said, first, I should say that I think dark matter is going to end up as a phlogiston, is that the word, of our times? Sorry?
Phlogiston, I think.
Phlogiston, yeah, could be that, of our times, a substance dreamed up to resolve an otherwise unsolvable problem and later discarded as science advances. But even so, here's my question. Since gravity seems to be the only force that interacts with dark matter, what happens when a black hole, the ultimate source of gravity, comes into contact with dark matter? Does it eat it? And if so, what happens? And if not, why not? I think we've had questions of similar style and ilk before, and I can't remember what Fred said, but I think it said doesn't matter, because dark matter and but I'm sure you've done your homework because I didn't.
Yeah.
I never did homework as a kid, so why would I start now?
Well, there seems to be evidence that homework is fairly pointless, actually.
Yes,
my partner's a primary teacher, and I think if she had her way, kids wouldn't have any homework, and at least until you're fairly well through secondary school. It doesn't seem to serve a purpose other than making some parents feel like their kids are getting properly worked, So, but on to something that I actually have expertise in rather than talking about teaching where I clearly don't. Dark matter's a really interesting one. I get what you mean with the phlogiston. I think possibly dark energy, I'd argue, is a bit more of a phlogiston thing than dark matter at this stage, because it's very clear that there is mass out there that is having an effect, but we can't see. And that's fundamentally what dark matter is. We can add up all of the mass of all of the things that we can see in the forms of dust and gas and stars and all the rest of it. And the gravitational pull within galaxies, particularly as you get further out into galaxies, is more significant than can be explained by the luminous matter alone. And that's where dark matter comes from. And we see its effects even if we don't see it. In, I guess, just the same way as back in the 1800s, astronomers saw the effects of Neptune's gravity perturbing the orbit of Uranus as it went round the sun, and we detected Neptune indirectly. And then people said, you point your telescope here because there must be a planet in this part of the sky pulling Uranus around, and lo and behold, we found it. And this is fairly fundamental to me as an exoplanet science person, in that the vast majority of planets we found around other stars, we found indirectly. We see a star doing something unexplained, we see it winking or we see it wobbling, and we infer the presence of a planet as an explanation for that unexplained behavior. And when you rule out all the other explanations, the one that's left is a planet, and Bob's your uncle, you've added one to the tally. And like we said in the earlier episode, we've now passed 6,000, so whoopee for us, we're doing really well.
Yeah.
So there's a lot of evidence that dark matter is a thing. And what it is, nobody really knows. There's been a lot of speculation. But what seems to be the case is that dark matter is something that interacts through gravity but doesn't interact with anything else. It doesn't interact with light. It doesn't impede light, because we see dust. Dust blocks light, so dust is not dark matter.
Yeah.
So what happens? Well, if dark matter interacts with gravity in just the same way as normal matter, then it will interact with the black hole in almost the same way as normal matter. And the almost there, the little asterisk I'll come to in a minute. What that means is that if something gets close enough to a black hole to be within its event horizon, then that means it would have to travel faster than the speed of light to escape from the gravitational pull of the black hole. So it's effectively been nommed, and you've got black holes being the Pac-Man of the universe that just go around gobbling everything up. Once it is gobbled up, it doesn't matter if it's dark matter or normal matter. It's been nommed, and it just adds to the mass of the black hole. And I guess a black hole's a bit like the Borg, and it's your individuality and distinctiveness has been added to our own, and the dark matter has been nommed in just the same way it would have been with normal matter. So from that point of view, there is actually no problem. We'd expect dark matter to be eaten and to stay eaten. There are suggestions that the supermassive black holes, like the one we've got at the middle of the Milky Way, are only able to be formed if dark matter exists. And even more normal mass black holes have a restriction on the amount that they can eat. It's almost like the celestial equivalent of a gastric band or something like that. It's something called the Eddington limit. Material falling into a black hole that is normal matter, as it falls in, gets accelerated, gets heated up, emits light. And if you've got a black hole eating a lot of stuff, there's a lot of material falling in, emitting incredible amounts of radiation that can essentially push away other matter around the black hole and force it to stop eating, effectively putting a limit on the amount that it can devour at any given time.
Right.
And you do get things that are eating at what's called super Eddington rates, but that's where something's essentially pushing material in so quickly that it overcomes that effect. So I guess it's a bit like saying you can only drink so much water because you can only swallow so much, but if somebody shoves a fire hose in your mouth, the water's got to go somewhere. Yeah. That's kind of that situation. But that puts a limit on how much a black hole can eat at a given time, at the pace at which it can devour matter.
Yeah.
Dark matter doesn't interact with light or radiation or anything like that, so the Eddington limit doesn't apply, because a black hole shining like a searchlight will not impede the motion of dark matter one little bit. And so there is an idea that actually dark matter is a more effective food for black holes than normal matter, because dark matter circumvents the gastric band, it circumvents this Eddington limit that prevents a black hole from eating to excess. And that may actually have been a significant part of how the supermassive black holes that we get in the middle of galaxies actually got their start, that they got their start aided by dark matter. And so it's a really interesting question, because I'd not really thought of this until Howard's question came through and I did a bit of reading around. But it's actually one of these scenarios where dark matter, it seems, is a help to black holes rather than a hindrance, and therefore may help to explain why the universe is the way that we see it today, beyond just explaining the rotation curves of galaxies and things like this, which is why it was hypothesized in the first place.
Okay, so you do believe there's interaction between dark matter and black holes?
Of course, yeah. Sorry, the of course there sounds dismissive. The reason that it's an of course is that dark matter interacts with gravity. That's fundamentally how we found it in the first place. And therefore, if it falls into a black hole, it behaves like any other kind of matter from the point of view of gravity. And so therefore, and I mean, there are some suggestions that black holes are a significant component of dark matter.
Yes.
We can only see them when they're feeding. If they're not eating anything, we have no indication of black holes there other than its effect on the mass around it. You know, light gets bent around it and all the rest of it. Yeah. So some component of dark matter may well be primordial black holes. That's one of the suggestions.
Yeah, there's still so much to learn. We don't know much at all. Although they also, I think, if I recall correctly, say that dark matter clusters in, around galaxies and around, concentrated points. It's much thinner where the universe is emptier. Is that right?
And that kind of makes sense as well, because if dark matter is feeling the effects of gravity like everything else, the same things that would have pulled an excess of visible matter together to form galaxies would have brought together dark matter as well. And there is this discussion that galaxies have dark matter halos around them. So the rotation curves of galaxies are evidence for dark matter within those galaxies, meaning that there is more mass interior to a certain distance from the middle of the galaxy than we can account for by what we see. that means that you get the rotation happening quicker because there's more mass and therefore more gravitational pull, so a faster rotation.
Yeah.
But the massive galaxy clusters, in terms of how the galaxies are interacting with each other and how they're moving within the clusters, the mass within the cluster has to be bigger than the masses that the galaxies seem to have from the visible material, even accounting for the dark matter in them causing their rotation speeds to be higher. And that's suggesting that dark matter is also in a halo around the galaxy, giving that galaxy even more mass and even more oomph.
Yes, it is so fascinating. And phlogiston was a hypothetical fire-like element once thought to be contained within combustible bodies and released during combustion, a theory proposed by Johann Beecher. And it's an outdated theory that was eventually disproved by Antoine Lavoisier through his experiments with oxygen, which demonstrated that burning is a chemical reaction involving the combination of a substance with oxygen, not the release of phlogiston.
Yes.
There you are. All right. Howard, thank you so much for a great question. Let's take a break from the show to tell you about our sponsor, NordVPN. And we're very proud to have partnered with NordVPN so that we can get you more secure online, no matter what you do, where you are, or how you do it. Now, if you sign up for a 2-year NordVPN plan using the code word SpaceNuts, you'll receive 4 extra months absolutely free. That's 28 months of top-tier VPN protection at a fraction of the cost. With NordVPN, what you get is access to over 7,700 servers worldwide, ultra-fast connections, advanced features like Threat Protection Pro and MeshNet, and secure usage for up to 10 devices simultaneously. So you're pretty well covered, you have to admit. Now, this is a great opportunity, and if you'd like to take advantage of it, visit nordvpn.com/spacenuts to claim your exclusive offer today. And remember, with NordVPN's 30-day money-back guarantee, it's risk-free. It's a great investment, a small price to pay for your online security and privacy. Stay secure, stay connected, and keep exploring the cosmos with confidence. nordvpn.com/spacenuts, nordvpn.com/spacenuts, and don't forget the code word SpaceNuts at the checkout. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, Gary is next. He's a fan from Canada's East Coast. I was only recently on Canada's East Coast. Visited Peggy's Cove and Halifax, a lovely part of the world. He goes on to say, I enjoy your humour mixed with actual scientific knowledge. Oh, well, that latter part's probably not true. Anyway, question, can you tell me if Betelgeuse explodes 680 million light years away, whether we are just seeing something that happened 680 million years ago, travelling at the speed of light?
Yeah, it's a really good question. It comes up a lot when I'm doing outreach and stuff like that. Betelgeuse is, depending on whose measurements you expect, it's not quite 680 million light years away. It's somewhere between about 500 and 700 light years away. So it's a bit closer to home than that. But the question still stands. When we see objects in the universe, we see them as they were when the light was emitted from them. And that's even true for the room around you. It's just that everything nearby is so close that you're effectively seeing it instantaneously. Light travels at 300,000 kilometers a second. So we see the moon, which is about 384,000 kilometers away, varying. We just had all the fuss about the supermoons yet again. So the distance to the moon does vary a little bit.
Yeah.
But that means we see the moon using light that reflected off the surface of the moon about 1 1/3 seconds ago. It's 1 1/3 light seconds away. We see the sun with light that left the surface of the photosphere a bit more than 8 minutes ago. Yeah. And so when you see anything, you're seeing light that left a period of time ago. You see everything as it was in the past rather than as it would be in a perverse now, that if you could teleport there instantaneously, it would look different. I mean, that brings into question, could you teleport at faster than the speed of light? But then the question is, can you teleport anyway? So that's getting into the grounds of science fiction.
Yes.
But it brings open a odd philosophical kind of question, which is, what do you define as something happening now? Do you define the now as the perceived now of where you are, or do you find now as being the time that the event happens, that the light would reach you once it has traveled that distance to get to you? And I'm explaining that badly, but this is essentially the fundamental of the question. If Betelgeuse exploded 1,000 years ago, and that light reaches us, say, 300 years in the future, so it turns out it was 700 light years away. Betelgeuse exploded 1,000 years ago. The light travels for 700 years, so it'll reach us in 300 years' time. And I'm sure my head has got flipped over there somewhere. But hang on, if Betelgeuse exploded 1,000 years ago and we saw it 300 years in the future, then that'd be 1,300 light years away. I'm going the wrong way. But anyway,
we know
it exploded in the past. We see it at some point in the future. Did that explosion happen in the past or the future? Well, in Betelgeuse's frame of reference, if you were stood camping near Betelgeuse, you would have seen it in the past. You'd have seen it happen already. But any signal you sent to tell us that it had have happened would only just arrive at the same time that the explosion did, because you'd have to see it first and then the signal back. So from the point of view of us here on Earth, when does Betelgeuse explode? Is it when we see it, or when we calculate back how long ago that explosion had to happen for us to see it today?
Yeah.
And it's where we get into the philosophy of perception and what it actually means to be now. Because everything around us, even the tip of my own nose, is far enough away that I'm seeing it in the past. I mean, I'm seeing it in the past by nanoseconds, but it's still in the past. And so there's a weird bit of internal philosophy that has to go on there that is driven by the size of the universe. And we come up with this fine with sound. We see a flash of lightning, and then we hear a rumble of thunder a certain amount of time later. And we're aware that the two events happened at the same time, but the sound takes a certain amount of time to reach us. So if we imagine that there was some form of instantaneous communication that could happen, that happened faster than the speed of light, and we were able to have a relay near Betelgeuse tell us, Betelgeuse has now gone bang, you will see it in 700 years' time, then it makes sense to say that Betelgeuse exploded in the past and we only see it now. But from your perception point of view, you'd see it happening now when you saw it happen now, and that will be your now.
Yeah.
And so this is a really fun question, because the reality is that it's all to do with frames of reference and where you stand. And yeah, I'm listening to a fairly pulpy science fiction series at the minute called Expeditionary Force that actually talks about how slow light is when you're having combat happening in space. You know, if you're shooting lasers and masers at people and you're a light second away from them, by the time your laser gets there, they'll have moved. Mm-hmm. So you've got to shoot where they're going to be, not where they actually are, but then they know that, so they're dodging. And the further away you are, the longer it takes for the light to reach you. So you've got the bizarre thing of, if you can jump through space and you can go through a wormhole and pay someone else, you could fight someone and then jump through space and watch the battle happen and watch yourself fight them.
Wow.
And this is where all the philosophy starts to mess with your head.
Yeah.
But it makes for wonderful science fiction scenarios, so long as you build something into your science fiction world that allows you to have faster than light travel, so you can get ahead of the images of yourself doing a certain thing.
That is really interesting. I love science fiction for that reason, because you can just make all this stuff happen that, you know, is not yet achievable as far as we know.
One of the most bizarre examples of that, when I was young, I remember the Anne McCaffrey novels really well. And, you know, she was most famous, of course, for the Dragons series, you know, all the books about people on a world where they live and bond with dragons and they burn thread from the end. It turns out that it's actually a soft sci-fi setting rather than a fantasy setting, because reasons you find further down the series. But she also had a series of books about the talents of Earth, which were these people with psychokinetic and telepathic talents who could transport things using the power of the mind from one place to another, and they could communicate telekinetically. And of course, what you do with people like that in Anne McCaffrey's world is not turn them into soldiers and warriors like Marvel or the X-Men would do it, but you turn them into the Postal Service. And the people effectively become the method by which we send people to other stars. And if you're a powerful enough telekinetic, you can pick something up on Earth and send it to Capella, and it'll appear there. But then they had really powerful telescopes, and they'd have had to be really powerful telescopes the first time they tried sending things to another star. And they'll look at that star, and psychic person goes wibbly wobbly, and the thing disappears, and then it appears next to Capella. And that's all well and good until somebody points out the fact that the light we're seeing from Capella left it 30 years ago, and we've just seen that thing arrive, so they've obviously teleported it back through time. And then you end up with this bizarre world where you've got this web of worlds at vast distances from each other that are linked by these postal service workers, effectively, who can foment instant communication and instant transportation. But in order to have it be instant and to maintain the current now, they've had to send things back in time. But that then means if they sent them back in time, but they can communicate instantaneously in both directions, could they tell you 30 years ago to not send them?
Yeah. Yes. It's a similar story in terms of the Dune sci-fi series, because same thing, they fold space, so you can go instantly from one planet to Dune. But based on what you just said, that's not the case. They'd have to be going back in time as well.
Yeah, and the Anne McCaffrey stuff got that part right, but then you do have that thing of, if it can communicate instantaneously both ways, then you're communicating back in time by 30 years. But if they then looked back at Earth, they would see Earth as it was 60 years earlier, because they're 30 years back in time looking back 30 years. It strikes me that with big enough telescopes that would... I mean, it's a science fiction world, so we've already broken the laws of physics. But you would make detective work and police work totally redundant, because what you'd do is you'd say, there was a crime last night. Right, we'll teleport someone 14 hours away, so they're looking back 28 hours, and they can just look back and see what happened.
Yes. Yeah, it makes... Yeah, I love it. I love these impossible scenarios, but... one day they might come up with a way of doing some weird stuff that we can't explain today, and there'll be some logic attached to it. But
I'm sure if we were podcasting 125 years ago, people were convinced you couldn't have a heavier than air flight. And look how that worked out.
Yeah, exactly. All right. Thank you, Gary. Hopefully we covered that question for you. This is Space Nuts with Andrew Dunkley and Jonti Horner.
Okay, we checked all 4 systems and skiing was a go.
Space Nuts.
Our next question, we're still in Canada. This question comes from Mark.
Hi, it's Mark in London in Canada. I'm currently listening to all the back episodes, so I'm in March 2021. So if you answer my question, it might take me a while to hear it. But I was wondering about Lagrange points and the way they're described as a gravitational well, and we can send satellites there to orbit around them. Is there a way to define the mass of a Lagrange point? Like, obviously, there's nothing there. It doesn't actually have a mass, but we define or we observe things orbiting, and we can define the mass of all those objects. So when you see a satellite or design a satellite to go into orbit around a Lagrange point, is there an equivalent mass that it's orbiting that's obviously created by the whole system of the larger objects? But does that mass, is it definable? Thanks. Bye.
Thank you, Mark. See, Mark's actually demonstrating time travel. He's listening to us in the past, but we're hearing him today.
I was just thinking of that. So the question is, when Mark listens to this answer, is he listening to it in 2025 or 2029? Or
yeah, that's a good point. Very interesting. Thanks for the question, Mark. So we're looking at Lagrange points. Our next question actually kind of focuses on that as well. Lagrange points, gravitational wells. The mass of a Lagrange point, I think, was the guts of his question.
Yeah, and it's a really interesting question. In fact, I've got a PhD student, part-time student working with me who asked a very similar question a couple of months ago, because he's going to be looking at the Neptune Trojans, which are trapped around the L4 and L5 Lagrange points of Neptune, and they'll vibrate around following this kind of kidney-shaped path over a period of hundreds of years around this point 60 degrees ahead or behind Neptune in its orbit. What's going on here is... Well, take a little bit of a detour. When I was a kid, I was a member of the Scouts. And
me too.
When you were in the Scouts and you went walking around the countryside, you had an Ordnance Survey map. And I don't know if that's called the same thing overseas, but that's what it was in the UK. And what this map had was a map of all the roads and all the hills and all the rest of it, but drawn on it were contours. And all points on a given contour were the same height above sea level.
Yep.
And so you could tell how tall the hills were, how steep the valleys were, all the rest of it. What those maps actually are maps of gravitational potential. So all objects at the same distance from the center of the Earth have the same gravitational potential, and you join them up with a contour. That's exactly the same thing. So if you make a hypothetical simplified solar system where you just have the Earth, well, the Earth and the Moon smushed into one, and the Sun and nothing else, you can make a contour map where you measure, where you calculate the gravitational potential at every location in the solar system, and then you do the same kind of map. You join the points that have the same gravitational potential by a contour, and you get a contour map. And that is fundamentally the same as your Ordnance Survey map. Points that have the same gravitational potential would be metaphorically at the same altitude above sea level, same distance above sea level in the solar system.
Yeah.
Now, if you draw a line directly between the Sun and the Earth is at the bottom of an enormous blooming hole. You know, the contours are circular around it. The Earth is at the bottom of a smaller hole. And this is where the whole metaphor of weights on a rubber sheet, bowing the rubber sheet comes from.
Yes.
So the Earth is at the bottom of its own hole that is smaller than the hole that the Sun makes. And so if you have a line between them, you effectively come uphill from the Sun until you reach a certain point, and then you tip over and you start falling down the Earth's hole, so you go downhill again. So between the two, you've got like a saddle point, where at the top of that saddle, you're at a flat point where space's gravitational potential is flat, and you could balance there. You could put a marble there and it would sit there. But if that marble goes slightly off in either direction, it'll roll down the hill. So if you get a little bit closer to the Sun, you'll fall off and roll towards the Sun. If you get a little bit closer to the Earth, you'll roll off and roll towards the Earth.
Yeah.
Now, if you move out from 2 dimensions between the Earth and the Sun to 3 dimensions, if you roll clockwise or anti-clockwise away from that saddle point, you'll actually be trying to roll uphill, so you'll fall back down into it. So you've got this kind of, really is like a saddle point where towards the Sun and towards the Earth, you fall downhill, but at right angles to that, you try and roll uphill. So you've got this local flat area where if you move a little bit ahead or behind it in your orbit, you'll roll back down. So you've got a bit of a restoring force there, but if you roll inward or outward, you'll fall off the hill. And that's why that Lagrange point is an unstable one. It's like a saddle point. And the 3 Lagrange points that are on the line between the Earth and the Sun, L1, which is between the Earth and the Sun, L2, which is on the far side of the Earth, beyond the Earth, but on that line, and L3, which is on the far side of the Sun, opposite the Earth.
Yep.
Those points are all these kind of saddle points. So they're a bit more stable than normal space because you can imagine balancing on the flat part of the hill. But if you roll in either direction, you fall away. Now, a lot of our spacecraft sit at the inner or the outer Lagrange point, L1 or L2. The ones at L1 sit there because they can observe the Sun and give us prior warning if something's coming our way, solar mass ejection, something like that. The ones at L2 sit there to be in a good position to observe space, but have station keeping with the Earth. They move around with the Earth. And that's things like the James Webb Space Telescope. But because those locations are these kind of saddle points, they're not perfectly stable. Those spacecraft have to have fuel to stay on station. So if they start to drift downhill, they can push themselves back up and get back to the saddle point. And they actually do this by wobbling and vibrating around that point and have a little orbit. The other 2 Lagrange points are L4 and L5, are 60 degrees ahead and behind the Earth in its orbit around the Sun. And these are like enormous flat plateaus. If you look at a contour map of the gravitational potential in the solar system, you get these big kidney-shaped areas that are pretty flat. And that means if you have your ball there, it could just sit there. And even if you're quite a long way away from the center point of that Lagrange point, you'd sit on one of these contours, and if you started to roll, you'd follow the contour around and you'd follow this kind of kidney-shaped path, staying trapped around the Lagrange point, but vibrating around it. And they're like plateaus, so they're much more stable than the kind of saddle points. And that's why those are the points which, in the outer solar system, have huge populations in the orbit of Jupiter, have big populations in the orbit of Neptune. Those are the Jupiter and Neptune Trojans. The other planets can have Trojans too, but they tend to be temporary because the solar system's not simply 3 objects. it's actually got all the planets. So if you're sat near the Lagrange points of Earth, you're getting gravitational pulls from Venus and Mars nearby, from Jupiter and all the other planets as well. And eventually they'll pull you off the stable plateau and you'll fall away. So you'll only live there temporarily.
Yeah.
But for Jupiter and Neptune, those planets are so dominant compared to the other things around, they can hold things permanently at these Lagrange points. And the motion of objects at the L4 and L5 points is that over hundreds of orbits, they will gradually librate around that L4 point. So they'll be, on average, 60 degrees ahead or behind the planet, but they'll be moving around that and they'll be orbiting it. So the concept of trying to think about whether you can define a mass at the center of the Lagrange point that holds them, it's not quite the physics that's going on. That librating around that point only works if you're in a frame of reference that is rotating with the orbit of the planet. So let's imagine we're looking at the Jupiter Trojans. You imagine you somehow suspended above the plane of the solar system, lying there watching all the objects in the solar system, and you're spinning once every 12 years, just as Jupiter orbits the sun once every 12 years.
Yep.
So from your point of view, Jupiter and the sun stay in exactly the same place in your field of view. And then over much longer timescales of hundreds of years, these Trojans would appear to orbit the Lagrange point. I guess you could, if you wanted to, try and construct some model to visualize that, where you imagine that there is a virtual mass at the Lagrange points, and that's what the Trojans are orbiting while they librate. It would have to be a spread out mass, because if it was a point mass, they'd have much more circular orbits. They wouldn't have these kidney-shaped things. So the mass would have to be spread out. But you could, I guess, visualize it and calculate it. But that would only be valid in the rotating reference frame, which is a bit of a conceit anyway. In the normal scheme of things where everything's rotating around and you're not spinning above watching it, these objects are moving on orbits that are very similar in period to, say, Jupiter, but slightly longer or slightly shorter. And as they pull, if it's a slightly shorter orbital period than Jupiter, gradually they'll inch ahead of Jupiter, get further and further ahead. And eventually they drift outwards and they're now further from the sun, so they're now going around the sun slower than Jupiter, and they start to fall back towards it until Jupiter's gravity tweaks them and they fall inwards a bit, and then they start moving quicker. So it's actually all down to the interaction between Jupiter, the sun, and the object in that case, rather than a virtual mass off there. So I can see what you're thinking about, and I can see it as being something that is a good model to help you visualize what's going on. But it's not the kind of thing we do calculations of, and I don't think it's a sufficiently advanced mental model that you'd want to get to that level with, because it starts taking you down a rabbit hole of the physics doesn't actually work that way, and you can put yourself in traps when you do that. But it is a really nice way to visualize initially how it works. It's, if you're librating around one of the Lagrange points, it is as though there is a force keeping you trud to it. So it's as though there is a mass there attracting you towards the Lagrange point. It's just that isn't actually a mass there. It's simply to do with the interaction of all the other objects floating around that create that virtual thing that keeps you locked around that place.
Mm-hmm. Okay. Hopefully that helped you out, Mark.
0G, and I feel fine.
Space Nuts.
And our next question and our final question kind of relates to this question that Mark raised, and this came from a YouTuber. I don't know their name, but that's okay. Can you do a deep dive on the Kordylewski plasma clouds, or do we not have much information on these strange things? Now, I looked them up. The Kordylewski or Kordylewski clouds are two large, tenuous dust clouds located at L4 and L5 Lagrange points of the Earth-Moon system, originally predicted in the 1950s, first spotted in the 60s. Their existence was long doubted, but recently confirmed in 2018 by observations using a polarizing filter that detected reflected sunlight from the dust. While they are called dust clouds, some research suggests they are a complex form of dusty plasma.
Yes. So this is a fascinating question. The Kordylewski clouds are transient, and I think that's probably part of why they've been hard to confirm, because there are areas where, as we just described, those Lagrange points, if you only have the Earth and the Moon in space and nothing else, then the leading L4 and L5 Lagrange points of the Moon could be stable on million-year, billion-year timescales. But in actuality, we're in a system where you've got the sun, you've got all the other planets, and for small objects, the influence of the solar wind and the sun's radiation becomes significant as well. What that means is that it becomes easier to escape from those Lagrange points. By being easier to escape, it also means it's easier to get trapped there in the first place. Because if you can get out, you can get in. And so what that means is you can imagine as the moon and the Earth are orbiting their common center of mass, 60 degrees ahead and behind of the moon are these areas of space in the moon's orbit that are like little dimples in space, where it's easy for stuff to build up and get captured there temporarily before getting cleaned out again. They're not deep enough for things to get hooked there permanently. But what that means is that interplanetary dust, bits of the solar wind that aren't moving that quick, stuff sputtered off the moon by impact events, some of that can congregate there and spend a certain amount of time there. Now, the dynamics of it are such there's been a lot of modelling done of this, that if dust is there for a reasonable amount of time, it will actually get congregated into kind of bar features and streams. I think you'll actually get a bit of structure in it before it gets cleaned out. But fundamentally, what's going to be happening is that you've got dust and gas getting temporarily captured there and then getting cleaned out again. And so the amount of material there will depend on what's happening at the time. These were proposed a good long time ago, and they were first kind of reported to be observed in 1961 by Kodolowski, and that's why they take that person's name. And got photos, observed them with the naked eye. They were about 2 magnitudes at that time fainter than the Gegenschein, which is just opposite the moon in its orbit, and is visible as a very faint fuzzy blob. So they're very hard to pick up, very hard to spot. And for many years after that, other people looked for them and could not see them. And that's where the controversy came about that they're probably not there. The much more recent observations by Hungarian astronomers made use of polarimetry to actually make these things easier to see. And they were able to see them. Now, there is, I would have thought, some debate over whether these have been there permanently since then, or whether what's happening is that the times have been detected at times when the dust and gas there has been a bit denser than normal, making them easier to see.
Yeah.
Because if this is a time-varying population of stuff there will be times when you see more and times when you see less. And again, PhD student of mine, and again, it's Jessica over in the US, she's talking with Aaron Bully, possibly looking at doing some modelling of dust ejection from the moon and where it would end up. And some of that dust would temporarily end up in the Lagrange points, become part of the Kodolewski clouds and then disperse again. So the evidence is that they're there. The evidence is that they're transient. The idea that there could be plasma there as well is just based around the same physics of it being an area which is like a little dimple where things can build up and be held there for a little while. And we're aware that when you've got a perfectly smooth floor, the dust stays spread evenly. But if you've got any little dimples and stuff like that, dust can build up there until a gust of wind blows it out. It's effectively what's going on there. So they're really interesting. It's quite likely that all the other objects in the solar system would have things like this as well. So Mars's moons, Phobos and Deimos, they're much less massive than our moon, so their Lagrange points will be much tinier, but you might get similar things there. We know that among the moons of Saturn, we've got a couple of co-orbital satellites, including a couple of satellites that actually have Trojan companions. So it's not just Jupiter and Neptune that have permanent Trojans. It's not just Earth and Mars, Saturn and Uranus that have temporary Trojans. There are actually Trojan satellites in the Saturnian system. And this is just one aspect of this. Now, you know, you could imagine that in a very, very different world, we could have had the moon and then we could have had a couple of smaller satellites, one leading it, one trailing it in its orbit. And it's quite possible that after the moon forming impact, there may well have been temporary kind of agglomerations of matter there on a much more substantial level as the moon was forming. You could have even had, you know, small objects being accumulating there, forming there, and then escaping and all the rest of it. But hopefully that covers stuff. It is a really fascinating topic. You know, the kind of imagery people have done to figure this out back then was really challenging. You're talking about using a very fast wide-angle lens and doing lengthy exposures to try and get a little bit of contrast between the brightness of the sky where the clouds are and the brightness of the sky where they aren't. The more recent work by the Hungarian team in 2018 did some very, very clever stuff where they not only imaged the clouds at the L5 point when they were there and did the polarimetry, but they also imaged the same part of the sky when the L5 point wasn't there. They also imaged it when there were some high clouds like cirrus there, when aircraft contrails were passing through that area of the sky, and things like that, in order to have comparisons from other objects that had in the past been suggested as giving false positives here.
Right.
And they were able to confirm that actually, no, it was the presence of the L5 point and the dust there was what they got, because it looked sufficiently different to the other things that it was robust, which is very, very cool. And it's a good example of when you're trying to find something that's incredibly hard to see and hard to study, then you need to do some really very impressive and very innovative observations to make that work. And, you know, people have done some lovely modelling of orbital mechanics to see how long things would reside there. And there've even been proposals of sending spacecraft there to check it out. But that's about where we sit with them at the minute. And it is a fascinating subject. We'll learn more in years to come. Doubtless when Jessica's PhD is finished and she gets to go on and do this further research, we'll learn a little bit more about dust that is kicked off the surface of the moon and where it goes and how that contributes. But like everything, you know, there's more to learn than we already have done, and we're still at the start of this journey, realistically.
Yeah, absolutely. Yeah, great question, and great to get a question from our YouTube audience, which is ever growing. So thank you for that. And we are done. Thanks for answering all those questions, Jonti.
That's a pleasure. It's good to get some kind of brain teasers and stuff that makes your head hurt a little bit. That's all.
It does, doesn't it? Yeah. I think we're Fred and I, and now yourself, are constantly amazed by the depth of the inquisitiveness of our audience. Yeah, I think that's a good way of describing it. But all right, if you have questions for us, and we could sure use some audio questions, we are thin on the ground, jump on our website and send them in. It's spacenutspodcast.com or spacenuts.io. Click on the AMA link at the top and you can send text and audio questions to us that way if you so desire. And don't forget to tell us who you are or where you're from, or both. Thanks, Jonti. We'll catch you real soon.
Yeah, looking forward to it. Thanks for having me.
Always a pleasure. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland, here in the studio. Couldn't be with us again today. He got himself stuck in the Lagrange point. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.